Okay, good morning everyone. So today we will continue working with the Maxwell equations, and the main focus in the second part of the lesson will be on transfer of energy and momentum through electromagnetic waves. This is a deep and very profound subject, so I encourage you to read about it whatever source, but especially, let's say, in Griffith's chapter 7 and 8. So the question is, how do we transfer electromagnetic energy, let's say, to heat, and what is the meaning of the electromagnetic energy? And this is, of course, important for everyday technology because we are transmitting always information through electromagnetic energy. So this is a very deep and profound concept. To start this concept, we're going to start with the statement, let there be light. Now, because you go to the beach and you sunbathe, you get light in you, and then you get all kind of either brownish or reddish, whatever, meaning you get energy. So obviously, light contains energy in a very deep way, in various complicated ways, actually, when you think about it quantum mechanically. But obviously, energy has been within you some form of light, and light is related to electromagnetic fields. This I assume you know, but we're going to see this, how this arises from the Maxwell equation. This will going to be, I would say, a standard exercise or standard maneuver, I would say, but later on we will try to understand what this means. So my goal is first to present more or less the math, some part of the math. It's kind of simple math, and later on discuss more physical ideas. So what we are going to consider is we're going to consider waves. Well, these are going to be electromagnetic waves in linear matter. So waves can also be transported in vacuum or in air, but also in matter. We are going to discuss it in matter. In Griffith's, I think it's mainly in vacuum, but it's very similar, provided that the system is linear. There are cases when it's not similar, which I'll briefly mention, and it will be later on in the course. So we are going to discuss waves in linear matter. And by linear matter, I mean simply that the relations between H, the auxiliary magnetic field, and B are linear, and similarly for the displacement and the electric field. This is going to be, so we have in mind a material that in principle, at this stage at least, has in it some magnetization and some polarization. It can be rather complicated, but it's linear, so it's not too complicated. And later on, we can simply say, okay, this material is actually the vacuum. We just take the constants there. You remember them, ER and μR, to be equal 1, and then we'll go into the vacuum. So if you don't like to think about matter, in some part of what I'm doing on the board, you can easily imagine a vacuum, if you like, if you prefer vacuum for some reason. So we also want to consider isotropic medium. Isotropic. So what I'm having in mind is some chunk of material where the x, the y, and the z direction are all the same. So I don't have, for example, different types of dielectric properties in x and y and z direction. So it's uniform, like the vacuum actually. This is a simplification, and it really helps us just reduce the number of equations. Now, I'm going to consider not how the waves are created. I'm not saying where they come from. I'm going to say let's solve Maxwell equations and find the waves inside. How are they created? In principle, you have some far away, let's say, charges, antennas they are called, that are moving and they are radiating and they are creating the waves. And this will be the subject of future classes, how to create the waves. You need some charges moving, and then there's radiation. This is a whole thing which is actually related to relativity, and it's a big, nice topic. I'm just assuming that we have some waves and we want to ask questions like, what is the dispersion of the wave? Is it a transverse wave, a longitudinal wave? These are the basic questions, and this you can get not by analyzing the sources or the boundary conditions. So they're far away, there's all kinds of things going on to create these waves, but we are looking inside the material. And this is relatively makes things very simple, and we delay how they are created for a later stage. Okay, so we are going to assume the following. First of all, the magnetic field B is related to the auxiliary magnetic field. This is just definition by this way. And the electric field, the displacement D is related to the electric field like this. So recall that B and E, I think you know what it is, and D and H are linear combinations. H is a linear combination of B and the magnetization field, and D is a linear combination of E and the polarization field. We talked about this many times, I'm not going to discuss it more. And here you see that I assume the linear medium, so B is linear in H, or if you want, H is linear in B, if you prefer it to think about it that way, and similarly for D and E. And these two constants, mu r and ER, are constants of the material, and if they are in vacuum, they are equal 1. And all this was already mentioned. Now here already you see something kind of weird, right? What is weird here? A little bit weird, okay, weird for me. You see, B is proportional to some constants times H, and D is some constants times E. But why did the great people define it in this way? Why not put E on this side and the other one like that? It's a bit strange way of notation, right? Of course, this is only a matter of definitions. We are just defining things. And soon you'll see why this definition actually later on makes something nice. And this is a good reason. But again, remember this is a definition because I can take all this junk, put it on the other side, and then I can put E on the other side, of course. But this is how we define things for some elegance, I would call it, that will soon emerge. Or maybe it's just historical way. Yeah, you had a question?
Yeah, first of all, how do I call H the auxiliary field in Hebrew? Because I can't find it anywhere.
Actually, it's very interesting.
Auxiliary.
How do you say auxiliary? I don't know.
Auxiliary is
yeah.
Okay.
But okay, I thought your question is different, so I'll answer a different question. You see, this guy is called a displacement. This, even in English, doesn't have a name like a displacement. It's called the auxiliary field. Mm-hmm. So I thought that was the question. Why this is called a displacement and this is an auxiliary field? First of all, I don't think you need to go into this too deeply. It's some history that, you know, you can ask ChatGPT if you want, but there is no deep reason. But, so this is called auxiliary. Auxiliary is a helpful field, something like that.
Okay.
I don't know the name in Hebrew, and maybe people in Hebrew would say magnetic field in matter, and this is just magnetic field, or something like that.
And another small question, just when we talked about linear materials, we said at the beginning that it's an approximation for weak fields. So I'm trying to understand, is the linear material, the linearity of B and D, is a property of the material or approximation for weak fields, or both?
Both.
Okay.
But many materials at weak fields behave like this,
okay.
but not always.
Okay.
And it's actually much more complicated than what I'm showing you. It's just, we always cheating you, and then the next level is to correct what we said before. You'll see this today. We saw it, for example, with the Ohm law, if you remember. So in reality, this mu r and ER can depend also on the frequency of the light and things like that. It's really complicated, and we are simplifying things here a little bit, which is applicable for some materials, but not for all. And that's a good thing, because that just means that nature is complicated, but we don't want to go into all of the complications. And as long as we understand what we are doing, this is of course fine. So what we want to do is solve Maxwell equations. Yeah. Mu and epsilon. Can they have a relation? That's a direction. Okay. This is what I said here, isotropic medium. So I am assuming here that the medium is isotropic in each one of the directions. In principle, if you have a lattice which has an x, y, and z coordinates based on the atoms, for example, a cubic lattice or something like that, you can have directionality in these objects. So think about dipoles. Let's say you have a lattice composed of dipole, dipole 1, dipole 2, dipole 3, so it gives you one direction. Then there's another direction. So yeah, they could be. But we want to simplify. We don't want to make things more complicated. What? There are two different things, isotropic and linear. Linear means that B and H are proportional to one another. You can have a linear material where this is not a number, or you can think about this, there are 3 components of B, 3 components of H, and then you have a matrix multiplying it. But that's still linear, because if the matrix does not depend on H, that is linear. You see, so these two things, you should think about them separately. These are two different issues. But we are assuming both for simplicity and also for beauty, otherwise the theory is really ugly. So what we want to do is we want to use Maxwell's equations. And now, of course, we have the Maxwell's equation which contain H and D. I think you remember that. But now I can change them a little bit because I can get rid of H and D because now I have B and E. So I'm working in medium, but still what I'll show you now depends only on B and E because of these linear relations, okay? So don't be surprised now, or don't be shocked, don't fall off your chair if you now see equations with no H and no D. So the first equation I'm going to use is dV equals 0. Now this just means that we are satisfying the Gauss law or the Coulomb law if you want, but the charges are 0. And this is another assumption that I'm assuming no charges. So this is, we are simplifying as much as we can in order to make things very simple. There are no charges. Now we have div B equals 0. So this is always, there are no magnetic charges. This is always true. So here there's no approximation or no assumption. Then we have Kel E equal minus dB dt. Okay, let's call this 1, this 2, this 3. This one is Faraday. No magnetic charges. Okay, this is a basic equation. And equation number 4, what we are going to use, what is the last equation, is the Ampere Maxwell equation with the Maxwell correction. But now I'm going to assume, like there's no charges, I'm going to assume there's no currents. So this medium, there are no free currents. So JF is equal to 0. And then what we are left is actually only with the correction of Maxwell. And then we use also this, and then we get this equation. LB equal mu r mu 0 ER dE dt. So here I assume JF is equal to 0. So the Ampere term, you are used to the fact that the Kel of B is proportional to B with steady state, with no change of time. That is well known. And now JF is equal 0, so now we are left only with this Maxwell correction written in this way. So these are the set of equations. And now we want to solve these equations for plane waves. So we are going to use an identity. The identity is this identity. Okay, so all these tricks, this is chapter 1 in Griffiths. I'm not going to prove them. This is equal, so the curl of E is equal to grad div E minus the Laplacian of E. So you see here there are two sets of derivatives in space, kind of complicated, and here you see, also two. The Laplacian is second order, and these two are also second order. And the important thing is, what is this? This is equal 0 because of the first equation. There are no charges, so this thing is equal. Just this is left. And what is the curl of E? So now we are going to use equation 3. The curl of E is given here, right? So this is the curl of E, so I'm getting here minus d dt curl B. So again, curl E is equal this because div E is equal 0, and then I need to take the curl because I took it here on this side, and I have the derivative, I change the order, and then I get this result. And why did I do that? Because now I can use equation 4. So now I see here, this reminds me, equation 4. I can see here the curl B, and then I can replace the curl B with the time derivative of E. And why is that good? Because here I have the Laplacian of E, and here I'll have the second derivative of T, and that is the wave equation. So when we do that, we get all this junk, and now you see why this junk is good, because all this junk is essentially one number. It comes together. If you add it on two, if I would define it in a different way, like here, okay, it will be on the other side. Of course, then I'll move it, but why move it? We do it from the beginning. We write it like this. And then eventually use equation 4. So this thing is proportional to d. All of this thing is proportional to the second derivative. And then I get the equation, which is a well-known wave equation. The minus and the minus go away. U0, dr, 0, second derivative of time. This is a very nice equation because in some sense, you see these are second derivatives in space, the Laplacian, and here we have second derivative in time. So time and space are now somehow treated on the same way, on the same level, second order, and this is a simple wave equation. Now, the same equation, just replace E and B. I'm not even going to write it. Same equation for B. You do the same tricks. You do the curl here, and then you invert the process. I'm not going to write it even. Now you see there are two equations, one for E and one for B, and both of them are well-known equations for E because these are wave equations. You know how to solve this. You solve this in wave in the course of waves. Okay, great. So now it seems as if the two problems are separate, but that is not true. That is not true because, as you see here, I used only these two guys, but there are also other conditions. These two guys. So the E and the B are not totally independent one of the other. They are related, and that is actually the physics. How E and B are related one to another. It's not that we have two equations, two separate equations. They live together because of the constraints, because we have four equations, not two equations. Okay? So this gives all kinds of interesting phenomena, and it answers the questions like, what is the type of the wave, longitudinal, or transverse, and things like that. So this is what we're going to see now. So now, so now what we are going to do is we are going to do something that you are familiar with, I hope, and if not, you should read about it. we are going to assume plane waves. So what I have here in mind, let us find solutions to these set of equations which are plane wave. This is called a plane wave. What we have in mind, not the boundary conditions, then we have all kinds of initial conditions, boundary conditions, whatever, then you can compose linear combinations of these waves together, add them up with the superposition principle. The superposition principle holds because these equations are linear. And then we can construct all kinds of wave packets, and maybe you land wave packets elsewhere, but now we are just talking about the plane waves. So what is happening here? K is the wave vector, and omega is, of course, the frequency. And there are relations between the two, and I think you know the relation, but I'll still tell you. We're going to think about, or the way I think about it, one of these parameters, K, for example, K, is kind of set. How is it set? You drive the system, and these are what I said, the radiation that comes from far away. So K is going to be a parameter that you use, and it's of course related to W if you want to write W of K. And the relation between K and W is called the dispersion relation. So what is, and now this is just proportional to, now we have to ask in what direction, etc. But here I already used an assumption that this wave is propagating in the z direction. It's a choice, of course. I made z special here. I could have chosen x, y, and z. I just called the wave is propagating in the z direction. Of course, you can do it in the other direction. This is nothing special. It's just convenience if you want. But there is a definition here already of a special direction, z, which is going to be super important. So now it's very easy to insert this solution into this equation, or into B. By the way, B will also be proportional to the same thing. You insert it in here, and what do you know? And you know this, I think. You have here the second derivative in space, the second derivative of time. So when you have the second derivative in space, effectively you are taking one k in the first derivative and another k in the second derivative, you'll get k squared. And you do the derivative with respect to time, you're going to take the frequency once out and the frequency out twice. So you'll have, like you have here, something of 1 over length squared, 1 over time squared. This will translate to a frequency squared, and this will translate to a k squared. And this already means that the dispersion is linear, that its k is proportional to frequency. This you can easily see, I think, from here. So k and omega are going to be related, and if they are related, there is some velocity that they are related. And this what is this velocity? This velocity is related to this coefficient here, of course. Because when I take the second derivative, okay, I'll get k squared. The I will give you minus on this side, and the other I another minus, because I squared is minus. And this, so roughly speaking, this object, what is it? It's actually 1 over the velocity squared. That's the velocity in which this wave is propagating. So you did this a million times, so I think you understand what I'm talking about. And I can say that the v propagation, the velocity of the, so this comes from here, the velocity is given by this object, mu r, mu 0. You can check it yourself if you don't believe me. E0 to the power half. And again, it's kind of obvious because, why is it half? Because of the second derivatives here.
Because of the wave equations, right? Because we know.
Yeah, but we have. So I mentioned before. Let's say that omega is proportional to k. That is true for this wave equation, but there are other wave equations, like Schrödinger wave equation. In Schrödinger wave equation, it's not true, because w there is proportional to k squared.
Yeah, because there is only first derivative.
Yeah, and second derivative. So wave equations for me, this is the most famous wave equation. That's true, but there are many waves equations.
Okay.
Schrödinger is also a wave equation. So this is the velocity. Now, what is this thing? If you want, this is a definition. And this is a huge surprise, and this is my kind of topic, let there be light. When Maxwell, or whoever did this for the first time, put in the numbers, especially mu0 and E0, and let's say he also put mu r and ER equal 1, he found here that this is, boom, the velocity of light, which is pretty amazing. And more generally, this is the velocity of light over n. So this is the speed of light, which we can measure. It's well known. And this n, this n comes in, for example, in the Snell's law. This is how waves break when they enter, let's say, from vacuum into material. In Hebrew, it's called Mekadem Shvira. And now I can't think how you say it in English.
Index of refraction.
Yeah, index of refraction, of course. Index of refraction. Thank you. So this is n, and just to be 100% sure, this is a definition of the speed of light. So all the rest, the n is related to mu r and er, right? You see this from this definition. I'm not writing it, but if you want, this is a definition, and this is a definition. So we have defined both n, and we showed that n is related to these polarization and magnetization of the matter through these coefficients. And now, so you can, in principle, somehow estimate what is mu r, what is, it's also magic. You estimate mu r and er, let's say, by applying an electric field, and you measure the polarization. You apply a magnetic field, and you measure the magnetization. You estimate what is mu r. And then you do another set of an experiment where you have light and you have the Snell law. And then that n that comes into the Snell's law, that I think you know, will be given by these two numbers, mu r and er. So you match up not only the speed of light, but also how light is refracted in the transition from one material to the other. And then obviously this is super deep, because this means that we are not, the name of the course is wrong in some sense, because it should have been called electromagnetism and light. But we think about light as electromagnetism in some sense. It's just light is for us some form of electromagnetic waves, that's all. Okay, so we have this beautiful deep connection. Of course, n is typically greater or equal 1. So, which means that the velocity in the medium is always less than the speed of light in vacuum. So, now the Snell law, for example, first of all, you know the Snell law, you know it from high school. This is chapter 9, together with many other applications in Griffiths. This will be in the homework and in the exercises, but I will not teach these applications. How you exactly derive, because what is the Snell law? I mentioned before, you see here in this setting, I would say, okay, I'm a professor, so I teach the easy stuff. So this is like in vacuum, in some sense. You just renormalize the speed of C, you renormalize it, and then you have a different speed, but that's all. It's small money, right? When you go and you have electromagnetic radiation impinging on a material, then you have the boundary conditions, and then it's a bit more complicated. And then you need to take into consideration, and then there is a big difference, of course, if you go from vacuum to vacuum or from vacuum to material, and that will be in chapter 9 and in the class. It's not so simple as presented here. So now, okay, so we have these predictions, and now we are going to ask in which way, in which direction E and B point. So we have the special direction z. Is it going to be in the z direction? Is it going to be in the x direction, the y direction? Some linear combination of all. And the answer is, just give you the answer and then we'll show it. It's not difficult to show. The fields E and B will be in the xy direction, but not in the z direction. And this is a rule of nature. And this is a deeper insight than this well-known thing. Maybe you also know this. But how do we prove it? So first of all, we have the field E, for example E, but also B, which is a function of z. Because this is what I assumed here. It's a function of z and not of x and y. But in principle, it has three components: Ex of z, Ey of z, and Ez of z. This, when I wrote here the proportionality, I didn't write here the vector. There is a vector. So this is these three components. And we want to say, for example, that E in the z direction, we want to show that this one is 0 for sure. So how do I know it is 0? I know it because div E is equal 0. This is this equation, which means that there are no charges in this problem. Now, if I take the div, for example, the derivative with respect to x of Ex, well, that's 0, because Ex depends on z, and similar with Ey. So here I get d dz, Ez. So this index z is the direction of the E. It's a function of z. This is equal 0. Now you might say, okay, maybe there is a function here of time. That's obviously also wrong, because it has to satisfy this wave equation, but let us show that this component is also the time derivative is equal to 0. That's also easy to show, even though it's kind of clear already from here. But let us just a little bit repeat. So let us look also on the time derivative of this component. So to go the time component, I go back to the Faraday equation. So let us write this. Okay, no, I'll do it, but I'll do it for, you can show it also for, okay, so from here, okay, Ez z is equal 0. The reason why this is only the space derivative is because of the wave equation. You cannot have a time prefactor or something like that of wave equation.
It's a constant, no?
It could be a constant, but a constant would mean k equals 0. And we say k is fixed. So what we mean here that if k is not 0, then the z component, which is the propagation, the direction of the propagation of the wave, is 0 in the z direction. And let us look at b, for example. So let us look at the time derivative now of b, and that is, we're going to use rotor E. Okay, we have x, y, z, ddx, ddy, ddz. Then we have E, x, z. E, we said already that z. These are maybe not 0. Ez, z. And let us look at the z component. Why am I looking at the z component? This is the direction of the wave propagation, and I want to show that the derivative of b in that direction is 0. So this should be equal, okay, in general it's minus db dt. In the z direction, z component, what do I have? I have to have this x, and then you see that you have a ddx eyz minus ddy ex of z, but this is equal 0, and this is equal to minus dbz of z dt, and that's why bzz is equal 0, again from the same argument as before, because the waves are these type of solutions. So if the time derivative is 0, then mk is not equal 0. This is impossible. So we showed that, what did we show? Just to summarize, based on these things up to now, we showed the following. The wave, that is the conclusion. The wave is transverse. So what it means is the following. I have here, this is the xy plane, as usual, very non-Michelangelo painting. And this is the z direction, and this is a plane. So this is the plane, this is the propagation wave, this is the z, and again, this is a definition of that we took from the beginning, and then the electric field and the magnetic field are in this plane. That is called the transverse wave. And you know that there's a longitudinal wave. This is, for example, pressure waves in a pipe. You have a pipe and you have some density, and then you can have a wave of density, for example, here high and here low. So what is so what is transverse here? It's the transverse of the electric and magnetic field compared to the direction of propagation. You can have a knot here. A longitudinal wave is something of matter. So this is a density. Or pressure density, and here there's low density, and then this thing moves backwards and forwards like that. And that is propagating in this direction. This is called longitudinal wave. And the point is, there's no longitudinal wave. There is a transverse wave for electromagnetic matter. And I think you studied this in optics or whatever. So, okay, so we know something about this wave, but we want to be a bit more precise, because we have, when you think about it, what are the waves? There are two waves here, E and B. And what? Okay, they are, and here I plotted them as if they are perpendicular one to another. And this is actually true. But at this stage I didn't show you that it is actually like that. Maybe they are in the same direction, maybe they are not. So let us show that they are actually perpendicular, that this angle should be 90 degrees. And this will end the characterization of these waves. Where is it? Oh, yeah. So for that we need to define, we defined the one propagation wave, but now let us make another assumption. And it's not a universal assumption, but it's done for simplicity. And that is, let us assume the electric field now is in the x direction. Why in the x direction? Because I want to, like I put the k in the z direction. Of course, we can do other things. I mean, linear combination of these things. The simplest thing is, let us assume that our wave is in the x direction. Later on, we can add all kinds of waves, and then that means the following, that E vector now depends on z and it depends on time, is in the x direction. First of all, it has an amplitude. What is this E0? It's not energy, it's the magnitude of the field. And what is this magnitude depends on what you put into the system. This is the amplitude. It can be big, it can be small. It's a control parameter if you want, like k. And here I add I k z minus omega t like before. And here I put the direction. It's going to be in the direction is. So again, this is a definition. By the way, I'm always using here complex values waves. Eventually, I'll sum many of them. I mean, it's not that the field can be complex. I'm going to add many of them and then get real valued waves. And again, this is standard. I think you saw it in many other places. But E eventually is going to be real by adding, For example, what I'll do later is I'll add a plus wave with a plus k and a minus k to get a standing wave and things like that. Okay, so this is the, if you want, this is a definition. And then the first claim is that Bx is equal 0. So what does it mean? That the magnetic field in the x direction is going to be 0 if the electric field is in the x direction. By the way, this now there is a kind of jargon. This choice that I say, okay, this is x, we say that the electric field is polarized in the x direction. This is what we are like doctors. Electric field polarized in x direction. Of course, we can have other polarizations. But why do we say this word? Why do you call it polarization? I mean, now we understand, because if it's a linear material, this is proportional to the displacement, which means it's proportional to the polarization, the macroscopic polarization. And from here comes the word. But if you think about it in vacuum, the word polarization maybe is a bit mysterious. But if you put it in material, it makes some sense, I hope. So this is, from here comes the name. The electric field is polarized in the x direction. This is just if some other guy will tell you I'm using a... Now there is an assumption here. Sometimes people will say on light, it is polarized in the x direction. What do they actually mean? Is that we define the polarization based on the electric field and not the magnetic field. It's just a definition. And the direction of the electric field is the direction that we call polarization. It's just jargon. So this is what is meant when you say light is polarized in the x direction or in the y direction or linear combination of x and y. This is what is meant, the direction of the electric field. And it all comes from the polarization field, because the polarization field in linear matter is proportional to E. This is really called polarization macroscopically. So, okay, so now you understand the word at least. Okay, so first of all, we see here that, first of all, E in the y direction is chosen to be 0. And again, we're going to use Faraday. So the Faraday, again, rotor E is equal x, y, z, d dx, d dy, d dz, E x of z, E y of z, E z of z. Okay, but what is this one?
0.
This is 0. And what is this one?
Also 0.
It's also 0. And this one is given up here. This is not 0. All this is minus dB dt. Okay, so let us choose the x coordinate, the x direction. So you see what happens here. The x direction, I have these determinant, right? Mm-hmm. But this is the y of something which is 0. This is 0. So my conclusion is that the derivative of b in the x direction, which is not the propagation, the z direction of the wave, of z, that is equal to 0. And as I said before, because the solution of the wave function, of the magnetic and the electric field are of this type, if the time derivative is 0 and k is not equal to 0, that it means that px and z is equal to 0.
This time it's because omega doesn't equal 0, right? Because we're looking at the time.
Yeah, but k and omega are linear, so yeah, it's the same thing. And what does this mean? And the conclusion now is that B vector is perpendicular to E, and both of them are perpendicular to K. K is the direction of the propagation of the wave, which was chosen at the beginning to be the Z direction. Now, if this is 0, what does it mean? It means that, this is what I'm writing here, I think it's obvious. If Bx is 0 and there's no B in the Z direction, so it's in the Y direction. This is what is written here. Why is it in the Y? Because I choose the electric field in the X direction, and the other guy is in the Y direction. And then this description that you have, let's say, if the up is X, then this is X, and then magnetic field is coming out of the blackboard. But now we have here this coefficient E0. And similarly for the magnetic field, you might say you have two wave equations, so you have some B0, some number, which is the amplitude of B0. But this B0 and this E0 are not independent. They are related, which is a nice thing. Then we don't need two amplitudes, we have only one amplitude, and they are related one to another due to the constraints that we have that eventually come from the Maxwell equation. So now what we want to do is we're going to use again this equation, but now we are looking at the Y component. If I look at the Y component, if you see it, the Y component is d dz dx. That will give you the magnetic field in the Y direction. And this is what we already said, that there is only in the Y direction. So there is a relation, because this one I know, it's this one. If I go again, Y, d, dz, like that. Hopefully this is not too much. Then I get the Z direction. So the Y direction. So what we have here is the following. From, again, Faraday. We have here from Faraday, now in the Y direction. Again, Y direction, because the By is in the Y direction. I showed this, so we are interested in the Y direction. Then we have the following equations. We have d dz, E, which is in the X direction. So this is this X here. And it is a function of Z. This derivative d of dz is again this one here. That is in the rotor of E. And this is equal to, and then there's a minus sign, I guess. Should be minus sign. This was the minus. Is there a minus sign? No, there's no minus sign, because this is a minus, but then this one is another minus sign, so there's no minus. But here there is a minus. Minus d dt b in the x in the y direction.
What are we trying to do?
We're trying to find the amplitudes, right?
Yes.
The connection between the
Yes,
amplitudes.
exactly. We want to. So we have again. We have this E0, and so I'll explain. We have here this Ex of z and By of z, which I didn't write, but it is exactly the same like this, but with B0 and Y. I take the derivatives here, so this guy will be proportional to what? To Ik multiplied by E0. So here I have E0, Ik, and then of course I have the exponent, but that will cancel out. Here we have minus the derivative acting on the b, so here I'll have a minus here, which saves me, and then I'll have here I omega b0 exponent I all the rest. I cancel them because the wave equations for the B and E are the same wave equations, so these two factors eventually are the same thing and same relation between K and A. So what I see here is that the ratio E0 over B0 is frequency over K. What is that?
C.
Not C, it's in matter, but nearly C, corrected C, the V that we defined previously.
C over N.
This is equal C over N equal V from the dispersion. Let's say N is equal 1, then the ratio between the E0 and the B0 is the speed of light. In that sense, if we work in natural units, C is big, so E0 is big in some sense.
So the amplitude
So-
of the electric field is much bigger than the amplitude of the magnetic field? Usually.
Well, it's a bit more complicated than that because you need to. What is the effect on some charge, right? I mean, in this sense, yes, but the consequences cannot
Yeah.
easily be translated because it depends on the velocity of the. If you put some velocity, high velocity in a weak magnetic field, the effect is big, etc.
Yeah.
So.
It doesn't.
I don't want to, I mean, you can say this in a different way. The most natural units that we should use here is the following units where the speed of light is 1.
Okay.
In that case, the E over B0 is 1, if N is 1. So then they are the same.
Mhm.
Because C is the natural speed here in this problem, right? I mean, in that sense, it's not true. But yeah, sometimes, okay. So just to summarize, okay, so these are the main equations. What we see, this is a summary. We had all this already. We have E is orthogonal to B. We have, okay, this is also already in the summary. Let's steal this. And then what I didn't write explicitly, so let us do it now, but I said it. Bz is equal, this is in the, okay, how do I want to write it? B0 exponential ikz minus omega t in the y direction.
Why can we assume that it's been described by the exactly same wave function?
This one.
Yeah.
This I mentioned at the very beginning, because the wave equation for E and B are the same.
Yeah, but
So-
what if they have different phases or I don't
They
know.
can have different
It
phases.
doesn't matter.
Yeah, I'm soon going to mention this. They can have a different phase, and of course, also the polarization, you can change it. It's just one choice
Yeah.
at this stage. We also mentioned direction of P of E is called polarization. The polarization of the wave. Polarization direction of the wave. Now you can, in principle, let us look and just draw this. Now, of course, up to now the waves were imaginary, but let us sum two waves. One in the plus k direction and one in the minus k direction. That is called the standing wave. Everything continues to follow because a linear combination of waves, if you have linear equations, is still a solution. And then we have two waves, just so we can plot it now, in the plus z and minus z, two waves propagating. So when I say propagating, I mean that is the direction of k, if you understand what I mean, and soon we'll elaborate on this. So we have two waves, one of them both for the magnetic field and for the, and then you have also exponential I wrote it previously opposite way, but okay. Kz minus omega t minus kz plus omega t. And I combine these two waves with the same amplitude together. If you want, then a linear combination will give you another solution. So this is a linear combination, which is given by some amplitude E0. It's maybe up to factor 2, so not exactly the same as before. So I write it with a hat. And in principle, now it's a cosine z minus omega t. And in principle, you can have a phase. And you can check, if you want, that, okay, and this is, but this is going to choose like in the x direction. So this is a linear combination of the waves, of the electric field. Again, as I mentioned already, there are also solutions, and everything I said up to now also holds for them. For example, on the relation between k of w, and you add a delta, it's fine, not a problem. It just means that this phase will continue for the magnetic field. It will be the same thing, but the magnetic field will have some constant B0, and the ratio will be like this. So nothing has changed. Why do I do this? Because now I have a real wave, I can plot it. And the plot, and this will kind of summarize what we saw here. We have here the z direction, we have here the y direction, and we have here the x direction. And then you see the electric field is in the z direction, so I choose some delta and some time, actually also some time t here. Hopefully this is clear. This is the electric field. So this just says that we are in the x plane, okay? So hopefully you see it. And then the magnetic field it's in the y direction. This is what I'm trying to plot here. This goes into the board. This goes out. Hopefully you have a three-dimensional vision better than my capability to draw it. So this one is the B. So you see that the wave is coming out of you, it's orthogonal. It depends on z, so it will change. This is for some given time. And then this thing is going up, and then the other thing is going inside the board. It's oscillating in time at a given position. This is what we called before. This is the transverse wave that describes these electromagnetic phenomena. Okay, any questions? No. Okay, so now we have this background of these electromagnetic phenomena. I guess we should continue because you are finishing at 11 apparently. You want to work. So, now we are going to discuss concept of energy for electromagnetic fields. So the basic idea is that electromagnetic fields, let's say I have a magnetic and electric field somewhere here in space. So I have some region here. In this region I have some energy. This energy can change. And this is important because we transmit information with this. How does it change? So how do we look at this thing? We will define soon an energy density, which depends on the density on the electromagnetic fields. And this density can change by different mechanisms. For example, if I have here electromagnetic fields, and then suddenly I turn them off, the total energy in this domain has been reduced. Or if the waves, I have here a wave of a packet of electromagnetic waves that are going in this direction, then if I look here, energy will go up and then it will go down and things like that, which means that we can control it if we can control it. This is very useful and very deep. So the fact that the electromagnetic field itself contains energy is highly non-trivial. But we saw it a little bit at the beginning, where we took some charges, we pulled them from far away, and we asked how much energy do you need to assemble a set of charge. So if you remember, we had one charge, we brought one in. This you do also in high school. Then you bring another one, and there's obviously work because you are bringing in charges from far away, and the first one is acting against the second against the first two, etc. So you put in some work. But where does this work go? It goes. We showed that it goes for electrostatics. We need to take the square of the electric field and integrate over space. That will give you the same amount of work. I hope you remember this equation that we had at the beginning. This topic will now be much more exposed and generalized. First of all, to include both also the magnetic field. Secondly, to discuss time-dependent fields. And thirdly, to discuss the transformation of energy. So energy on its own right is a very important concept. Energy of electromagnetic field, energy of kinetic energy, potential energy, etc., etc. All these by themselves are interesting, but also what is interesting is the transfer of energy from one to another. The most famous case in high school is kinetic energy to potential energy and things like that. So also here there's going to be some discussion on how you transfer energies, for example, to heat. So heat is another form of energy. And honestly, all these concepts, in my opinion, one of the deepest in physics. So you should really read chapter 7 and 8 in Griffiths. 9 is already applications, but 7 and 8 are the fundamentals that I'm trying to put here. And you should think about this a lot. You should talk to ChatGPT and whatever, Gemini, and it's very not trivial. At the end of this lesson, then I'll show you how non-trivial by solving some very simple systems and showing you how these concepts are translated to the more or less real world. But at the beginning, I'll just define it in a more mathematical way. So let us do this. So first of all, as I already mentioned, if I have a set of charges that were brought from infinity, so this is Q1, Q2, Q3, etc., we already said that the electric field is the integral over all space. So if I integrate over all space, this is the total work that is done by bringing them all together. And this is, it was E0 over 2, the electric field squared d tau. And this is a volume integral. So if I know the fields here, and I integrate over all space, I get the total amount of work to assemble this system. Great. But then I can think about this. What is this E squared? If you think about it, the E squared times delta tau is dx, dy, dz. The E squared in this equation is an energy density. Because this depends on a specific point. So at this point, we have some small box, and we have E squared. And what we are doing here in this integral, we are summing all of them up. So here there is an energy density given by the square of the field. Now this was for statics. So first of all, it's not only the assembly of all these things. I can think about it maybe as in this region, for example, there is some energy. What is this energy? You do the integral not over the whole space, but over this space. There's some energy, and if I do it somewhere here, there is another energy. It's just floating. We like energy. Energy is money, and money is power. So this is the concept that we are thinking about this maybe as a as a energy density, energy per unit volume. Now, however, this was derived in a static form. These energies that we had at the beginning were not depending on time, because at the beginning we had statics. Secondly, I think you added homework, there is another term. The other terms come from the magnetic field. I just mentioned this. Similarly, we have another term, W, let's call it B, or magnetic, 1/2 mu 0, integral over all space, or some part of the space. This is the total energy, and if I integrate over some of the space, it will be the energy in that space, B squared d tau. I think maybe you got it as homework, but I didn't teach it, but it's similar to that. And we are going to see these equations soon. They will come up again. So even if you don't remember derivation, you will see these equations soon. So I can think also about B squared as some energy density, which is related to the magnetic field, not to the electric field. And two of them are contributing. So then if we just look at some region, we have some region in space, so it has some energy inside, which is the total energy, which depends on this volume, depends on all the details. You need to integrate, it might be complicated. But then we can ask, how does this energy change? Okay, how does energy change? Well, if we look at these equations without doing the math yet, how energy changes inside here? It can be that you reduce the B and the E, or it can be due to some flux outside. So by changing the fields, change E, what does it mean? We have to explain. Or maybe the energy can just leak out. Why do I say this? I say this because, like some kind of continuum equation, if you want, the energy can be changed. Now, this is a bit, you say no energy can be created. Is that actually true? You need to think about it. When I say energy change, this is the electromagnetic energy. So what do I mean by electromagnetic changes? If something changes, it means it went to some other form. For example, it went to heat. So if there's no leakage of energy, no heat and no other forms of energy, some of these terms might be gone. Some of these processes that I'm not yet defining, but I'm letting you start to think about it, are defining. So we want to define, first of all, what exactly is the charge, what are these things? What is this density of energy? How is it related to leakage out due to, we'll call it radiation out, which is of the electromagnetic field. And then when we do the balance of all the energies, then you have other forms of energies like heat, kinetic energy, and you need to balance all of them together, because what is concerned is the total energy of the system, right? Not one form of energies. So kinetic energy by itself is not concerned. Now, how to balance these things together is for each problem you need to think what are the different energies, how do you transfer energy, etc. from one to another, and this is the difficult part actually. So we will have to think about this and discuss this a little bit, but you have to think about it a bit more.
So, we're trying to create some kind of continuity equation for the energy of the fields.
Yeah, for the energy density of the fields. For the electromagnetic energy density of the fields. And when there will be no other energies in the system, like kinetic energies or heat, it will be a simple equation. It will be really a continuity equation. But when we add and you can replace energies, it's a bit more complicated.
Yeah.
Because you have transfer of energy. And what does it mean, transfer of energy? Okay, you need to think about this. So this is done, of course, in Griffiths as usual. Griffiths does it in vacuum more or less with E and B, and I'm going to do it in material. But what Griffiths does is fine. I mean, you can read it in Griffiths. I just don't want to do exactly the same. So my derivation maybe is a bit more complicated because I add the D and the H, but I think it's very important because, for example, we can think about some material, let's call it a pipe or a wire, and inside you have some electric magnetic field and some current, and maybe this electric field is changing in time, so you are changing the density of the energy due to the electromagnetic field, but you're also creating heat, and for that you need matter, and that's why I like the matter here. But in principle you don't need this, and that will be simple because eventually, as before, we just say, okay, we are in vacuum and then everything will fall. I'll do that at the very end to get two formulations. Two formulations, one is in vacuum and one is in material, and both of them are important and very useful. So we go back again to the Maxwell equation, but now we have these are general equations, rho f. So D is the displacement field. We have equation number 2 is div B equals 0. We have kel E minus dB dt, which is Faraday. And we have here kel H, which is JF. This is ampere, and this is the Maxwell equation when we are in matter. Maxwell correction. So these are the four. At this stage, I'm not assuming linear. This is going to be general because this is fundamental. I'm not saying that the speed of light is not fundamental, but the speed of light is in vacuum, and then there's no material. So, anyways, so these are the famous Maxwell equation, and later I'm going to use div, and maybe some of you can guess why I need this. If either you read or you are very smart, or maybe just smart, maybe not very compared to Maxwell. E kel H. Why do I put this gun on the table, for shoot later, right? But why is this formulation useful, you think? This is the usual trick related. Okay, you will see if you don't see it now. This is a trick that was used here. Eventually, we want to go from all these kels that are in this equation and integration, etc., etc. We want to go to a boundary term in the integration to use the divergence, and then you'll have the flux out. It will come from that from this useful identity. And again, I'm not proving this. This is again chapter 1. You see here div, so you have only one operation of derivative, so it at least makes sense. Okay, so if you want to think about a specific problem, so we are going to talk about power or rate of work. So this will be, for example, the heat that you are generating. But it will be energy per unit time. That is power. You know power. Power you learned in high school. It's in units of watt. So this is a description of the. This will be the change in electromagnetic energy, which we want to define. So what I'm writing here in a symbolic way is simply the energy conservation. So here I'm generating some heat. Here the change in the electromagnetic energy, which we had before, but I need to define it more precisely. And then minus leakage out. Leakage of what? Of energy out. What energy? The electromagnetic energy. So here I have leakage of energy let's call it electromagnetic energy. And this is what I call energy conservation in this system, at least. If you are in vacuum, maybe this is zero because there's no heat generated. I mean, each electron is separate and it doesn't collide with lattice defects, etc. So it doesn't have anywhere to transfer its energy. And this is what I said before, that sometimes this is not here, or sometimes this is the kinetic energy. So you can change the kinetic energy. So sometimes you need to put all kinds of things inside here. So let us see how this works in practice. And one thing that you know is that the total work, that will be the work inside the material eventually, is FDL. Delta omega is, this is not a frequency, this is maybe this is capital D, capital omega, D omega for work, is FDL. And here I'm going to tell something that I think you know, that is equal, the basic thing is there is no work on the magnetic fields, which was mentioned, but let us just put it on the blackboard here. E plus V cross B. So I'm using here the definition of the force. There is some E and there is some B acting here. And this is multiplied by dl. And the whole idea is that this dl is the velocity times dt, the velocity field inside the material. So here I have some velocities, many things are moving here. Think about them as the free charges actually. And then you see here the following, that first of all, because the V cross B dot V is equal to 0, so there's no magnetic work. As you know. And we are only left with this electric node. But what is V times the rho? That is the J. More precisely, the J free. This would be also the free. This is just the work done on the free charge.
Rho is the energy density this time?
I didn't talk about energy densities. No, it's not the energy density.
No.
This is
The charge density?
the charge density, the physical charge density. You have, if you have more electrons or less electrons,
Okay.
and this in principle can depend on space and on time in principle. So the bottom line is that d omega is equal to J free, more correctly, E dot J, so it's E, V, again, V gives you the J together with rho. So V times rho is J, as I explained already previously. And this is multiplied by this delta tau, so this is an element volume, because you need the charge. So this is dx, dy, dz in some point in space. And now I have dt, which is good, because now I have, as time is increased, this omega is changed depending what is dt. dt is bigger or smaller, this can be more energy or less energy, etc. So this thing is just to give you what is the total work done on heat, essentially. What is dw dt? Now it's capital. This is small w. This is the whole work, the whole system. So I have a lot of elements, and this is my material, actually the material itself in which currents and things are flowing. Let us look at the integral of this to define, so this is equal to the integral over the volume that contains what? This JF, for example. E JF, J of the free charge, d tau. And this is just, if you want, what I'm defining here as the work. That's all. And you see what I did here. I did the work. Now, is this equation known to you? I claim you learned it in high school, but I'm just writing it in a different way. So what did you learn in high school, just to make the connection? Or maybe you didn't, I don't know what happened to you guys in high school.
P.
the power is equal to the current times the
Yeah, this is the same thing. This is the same thing, but in high school you learned something which they didn't say, that is of course for linear response to electric field. I can derive this in 2 seconds if you want. Do you want? But does everyone see that this is the usual I squared R for... You want me to derive it, yes or no?
Yes.
Yes, thank you. There's a brave guy in front. I hope they don't scold you later. So, in high school, okay, what do we say in high school? We have some material. And there is a current in this way. I, usually it's called, not J. So here we have J, but J is related to I, of course. What is J? I'm not going to write the vectors, but this is I divided by A. What is A? A is the surface here of this thing. This is A, and let's call this L. What else do we know? The voltage that you have in high school is what? Is E, the electric field, times L, right? Don't dare say not. But yes, this is the electric field, the voltage drop divided by L. So what do we have here in this dW? I write it in a big because there is an integral, dt. I'm doing this integral and the j is in this direction and then the jf is in the direction, the e is in this direction. So I'm using the fact that the j and the e are in the same way, and then I can easily do this integral. Okay, one thing is missing here. J is sigma times E. What is sigma? Sigma is the conductivity of the material, not the charge density. So if I do this integral kind of in a very easy to do it when it's a box and everything is very clear. So I know what is delta t. All these things are constants and they're all in the same direction, so it's trivial. So I have here, how do I want to write it? I have here, okay, so let us write it like this. We have here E, which is this E, and this E goes into V over L, right? And we have this JF, how do I want to write this?
I over L.
Wait, yeah, this is JF, which is I over A. But what is I? Yeah, okay, so now we have to remind ourselves. What is R, the resistance? The resistance is L sigma over A. And V is equal I R. So I can write, what do I want to write? I here over A. That's what I want to write. Okay, let us see. I over A. So I is, one way to put it, I is V over R, and that is V over L sigma A. So this is V sigma A over L. I didn't make a mistake.
Don't you wanna?
And then I need to multiply it by L A. This is not the best way to do things.
Don't you want to have I in your final end?
Yeah, I did. I have I because this is V over R. This is the I. Yeah, but better maybe leave I.
Just use
Leave I.
those two first equations.
Yeah. So we have here sigma V over L. This is LA. V over L is E. This is simply the J. And this, if you use all this, is simply, okay, you can do it later. This is simply, for example, I squared R, if I use the definition of R. Or you can write it in several ways, I times V, etc.
You can just use those two and simply.
Yeah, it's simple. It's too close to me. It's simple. So I just wanted to say that this formulation is what you know, but in high school we learn it for a very specific way, and the integration is over the whole box. Here it can be also on some part of the box if you want, but let's say philosophically it's the same thing. So what is new? The new thing is, of course, the maximal equations. So I know what is GF. JF will enter here. And this is exactly what we are going to do. So now we are going to write JF and use the scale H and D and the derivative here to find a relation between this, call it heat. This is when you, in some examples of this is heat, where you have a resistor and then you have a current and you put your hand on it and you'll feel the heat, right? It's getting hot, and this is the energy dissipation into the system. So, but this, the nice thing here is I can replace JF, you know, by H and D. And this step is introducing the fields inside this balance, because I'm going to throw away JF and write here the fields. And then what will be left? Well, you can more or less see, if I replace, I'll have the KLH and DD, okay, then I'll do some massage, but then on this side of the equation I will have, which will remain, it will be equal to something that depends on the fields. That something that depends on the fields is what? Energy of the fields, because there's no JF, there's no heat, there is no thing, and then we can also later on change the domain of integration. You will see this later. So for example, if this is the whole volume, this is something you need to think about. Let us say this integral, the total heat dissipated in a volume. But now let us say I want to make it bigger, the integration domain bigger. Is that allowed or not?
Yes.
It is allowed because JF is equal to 0 outside the domain. So I can change the direction of the integration on this side of the equation. And then what will happen here? There will be something else with the integrals over these things. I can also change there. And that is really magnificent, because I can do the integration over the fields, not inside the volume itself, but outside, somewhere far away if you want, where the integral might be either simple, or, as I'll explain it again a bit better, or if you can integrate far away only over the fields, then if you know the fields far away, or you can measure them far away, you can say something about the heat inside the system, which is a beautiful thing and a very deep thing. So it's totally, in my opinion, totally not trivial. So this is what we are going to do. Again, replacing this JF inside here and then doing massage with this thing and then getting some magic, in my opinion. So let's do it, but the math is rather simple. So this work on a specific volume, the capital W. The capital is, again, because I'm integrating, so I have this big letter, unlike this small one here, M is equal to the following, the integral over the volume. So I'm using equation 4. So this is from equation 4. I'm just replacing the E, the JF with this thing. So I have here the following. I have E KLH. E is remaining. Minus E dd dot dt over the integration over the volume. You see what I did here? I took this dd of the t to the other side of the equation. It got a minus sign. This is the JF, KLH minus ddt, and then you have the E, which is this one, and this is this and this is the JF, and we have the dot in the middle. Okay, this is pretty simple. Now we of course need to use this equation, but this equation contains this E KLH. So I'm doing here what at first might seem silly. I have one term, but I'm now going to create two terms out of one term. Looks like I'm making things a little bit more complicated. But what is the advantage? Now I'll have this div inside. This div will be integrated over the volume, and then you know how to integrate a derivative of some function over the volume. It will just give you what's in here and by the divergence thing, and then I'll have here, the other term will be H cal E. Okay, now up to now I used only 4. It will be H cal E. But cal E is this thing. So I'm going to use, of course, also a equation, the Faraday equation. So let us do this using Aleph. So from Aleph, I have here E cal H. So I have here, I'm putting this on the other side. So I have H. How do I want to write it? Yeah, H cal E. I'll leave this term now because this is a bulk term, ddt. This is over the volume, and minus div E cross H d tau. And this term is simply this term. Actually, in general, this is more or less it. This is important equation because there's no currents inside, in principle. Now, no, not this one, the next one, because cal E is minus dB dt. So d dW, that is the Faraday, is equal to minus H dB dt plus E dd dt. And this is already a little bit symmetrized because you have HB ED with one-time derivative, so we are happy with this. This is integral over the volume d tau. And okay, at this stage I'm going to write it with plus div, because I have here the minus, so this is this thing, E cross H d tau. And we know what to do with this thing. So now this is an equation which is important in general. And this thing we can simplify, and I'll soon do that, but I'll do it in one stage. So first of all, let us do it for linear material now. So for linear material, if you think about it for a second, E dd dt, so this is general, but this is linear, is half d dt E dot d. Okay? Why? Because d is proportional here. D is proportional to E times a constant. I can put the constant outside. And then I can take the derivative of of ED, and then I'll get out the 2 outside here. I can also write D as explicitly with ER and E0 as D, but this is very easy to understand if you put in the definitions of a linear material. And why do I do that? Because I want this time derivative here and here to go outside. Why do I want to do that? Because I want to integrate over something which I'm going to call the density of the electromagnetic field. So after you convince yourself that this is correct, and then you do, with this guy, what do you do? The divergence. You have an integral over the volume of the divergence. You integrate over the surface of the body. You reach the final final thing that I want to point out. It's not exactly the final, it's actually the beginning. D dt over the volume of the material that we integrated over is d tau, and here I have half ED plus half BH. It's the same thing because it's a linear material now. D tau minus, because of this minus sign, the integration over the surface of what? Instead of this div, we have E cross H, but now dot dA. So I have here some surface, and I have these patches on it. Each one is dA, vector outside, and EDH gives you, there is some E and there's some H, but only on the surface. You don't care what happens inside. You need to integrate all these contributions, and this will give you the change. And now you see several things that I mentioned before in a picture way here, based on this equation. First of all, you see here it's E dot D. So if you're in vacuum, what is it? It's E squared. This is what you studied at the beginning of the semester. So you see here E squared and you see B squared when you are in vacuum, which is something you know. Here you see, in general, it's E dot D and B dot H. This is what we are going to call electromagnetic density, energy density. So energy density. It's the electromagnetic energy density in matter. What would be the energy density in vacuum? The same thing, but half E squared plus half B squared. I think it's very clear that this is an energy density, because what we're doing here, we're integrated on some volume. The volume can be anything. You can choose the volume. And this gives you, the time derivative gives you the change of the energy. So this is the energy, and this energy can change in time. How does it change in time? You change the electric field, you change the magnetic field, so it changes in time. So this gives you the energy density, and this is what I called here this term. And then you have this term, but this is a surface term. And this is some flux that is going outside of the system. And according to this mathematics, it's E cross H. So you need to find this E, you need to find this H, and remember, for at least for plane waves, E and B at least are perpendicular. So soon you'll understand what is the direction, at least for a plane wave of this E cross H or E cross B. It will be in the K direction, where the thing is moving perpendicular to both E and to B if this is a vacuum. Okay, so you see the interpretation, and this interpretation is this is leakage. I call it leakage. When I say leakage, it could be it's leakage of electromagnetic energy. It could be leakage coming in or going out. It can be in both directions. So when I plot it here going out, maybe here it's going in. There's no special thing about going out or going in. So this vector is super important because it's the vector that describes the flux of energy that is carried by the electromagnetic field. And this E cross H has a name, and this is called the pointing vector. And pointing is another P, which is not polarization. So it's not polar, so I like to call it point. His definition, it's E cross H in matter. It describes leakage in or out of actually a point because this depends on x, y, and z, and t of electromagnetic energy. What happens if you are in vacuum? Then it's a bit simpler and more elegant maybe. Then it's very simple. We only need to replace H with B, D with E, and we are done. And H with B here. So now imagine a different situation where we have some change of energy. It could be different types of energy, not necessarily heat. This is equal to d dt integral over half E squared, that's E dot E B squared over the volume d tau integral over the surface of the volume E cross B dot dA divided by mu 0. Where does this mu 0 come from? Remember the definition of H and B gave you this
Must be u0 and epsilon 0.
yeah, sorry, this is my mistake. Epsilon 0 and here over u0. And this was already at the beginning of the class when I mentioned this part of the equation was derived previously with the epsilon 0, and this one I also mentioned with the u0. Now, this vector, so what does this describe? I have here some charges moving in some way, it doesn't matter. And then, okay, if there's no heat, then this is 0, and then there's only, or maybe there's kinetic energy change. And then there's changes in the density of the electromagnetic field and fluxes out of a surface. And then you have these balances of energy, but it's all done in vacuum. There's no polarization, there's no magnetization here. But this is true. And this is what you do with your cell phone when you transmit information more or less in vacuum. You are kind of moving, and then some energy is transported to your friend, and you can send nice pictures of cats and talk to one another. Now, hopefully not confusing, but this in this formulation, this is called, the Poynting vector is just this one. Which you see, it's exactly the same like before, but now we define it with E and B. Because there's no matter, there is no polarization, no magnetization. So these are the two definitions, and you need to know to jump between in matter and out of matter between these two formulations. Now, if you understand these equations, they are written on this side with an integral. They are not local equations in the sense you are integrating over something. But if this is a density, or this is a density, and this is a flux, you can understand that you can write this as in a continuum as a partial, as a derivative. Like we did similar things, or you did similar things, or I hope you did similar things, when you have the continuum equation for just material density. So you can write it as a differential equation, or you can write it as integrals over some specific volumes. The specific volumes here are useful because, let's say you want, what is the total heat created in this resistor? So we want to integrate over the whole material, for example. That's a good thing. But it's not local. So the local equation, local in space and time, give you, at a given point, what is happening, and very small, if you want to think about it as in a very tiny, tiny box, what is happening very locally to the energy. But going from these integrals into into a differential equation is rather easy. So the way I'm going to write it, and if it's not clear, you can ask questions. The way we can think about this. So let us work in vacuum, and let's change a little bit the agenda, not thinking about heat anymore. But there is some, beyond the electromagnetic energy, let's say the system has some mechanical energy. That can be kinetic energy, whatever. Okay, so in addition to this, there is something else always. Here it was heat, is power. And let us say there is something else. Why do I do this again? Because now I want to work in vacuum. Or vacuum thinking. And this is where the books are kind of jumping between two ways of thinking about things, and you need to think about this thing. So we have here, so when I talk about vacuum, I talk about this definition of S and this equation. And so I'm going to define, so I'm just going to write it down. So we have some, so as already mentioned, we have some surface at the beginning with dA, and there is some leakage S of this electromagnetic part of the energy. It's not all the whole energy. And then the claim is that the energy density, U electromagnetic, but there could be, in principle, some other form of energy which I'm going to call mechanical. And here is the difficult part in each system where you need to identify what that means. Okay, if there's no mechanical energy, it goes away. For example, in vacuum, there's no mechanical energy. So if I have here some springs that are radiating, then here there are mechanical energies. But if I'm working here, far away, there are no mechanical energies. You're in the vacuum. Totally, what I mean totally in the vacuum is that there are no material there, so then you can throw away that. And that is the transmission of information. When it's created, you transfer energy, right? And that is this, what I call biomechanical. So what is the U electromagnetic? Again, that's the energy density. And what is it? You have it here. It's written. It's half epsilon E dot E, which I write as plus U0 B squared. So I'm using the fact that this whole thing is an energy. And it's dt, it's sometimes some energy density. So this guy is what I call...
It's divided by mu0, right? Or
yeah, sorry. Divided by mu0. And what is U mechanical? You can think about it as the mechanical energy density. That is, if you think about it as springs, then each point of velocities, each point has some velocity, so it's delta function in some space for this particle. I'm not specifying it to the bitter end. And then if I look at this term here, then what do we have in a continuity equation? You take the integral, this will be like, what is this like? This is like a current of
a flux.
A flux, exactly. This is replaced by minus div S. So this is the flux, but the flux of what? Of essentially energy. It's a current of energy that the whole modern world is built on.
So this is the differential form.
Yeah, this is simply the differential form of this. If you want this, U mechanical is what goes in here locally in some small volume. So let us now start the lesson in the sense of explaining what this means, because this is not trivial. So I'm going to give you food to thought about, to think about what it means. If you want to go, you can go, and then I think it's recorded. You can listen to me later. You want a break now, or you'll not come back? Because what I'm going to explain now is, in my opinion, the beginning, here I just derive things, I just explain things, but now we need to think about things a bit more deeply. Okay, it's a bit late, so maybe I'll skip one example and I'll maybe at the end mention it. So first of all, we say that in the electric fields around us, there is energy. And this should be, I guess, in the beginning of the 20th, I guess Edison was very happy about this, and other people. And but what does it mean? Can we explain it in the most simplest simplest way that I could imagine? And okay, I managed to cook up some very basic basic thought experiment, I'm going to call it, that will show you that yes, indeed, there must be some energy density, because you say this is too much math. This is a lot of math, actually. Maybe simple math, but how can we more like a physicist think about this? And I'm going to do this by a simple experiment. Not that I'm doing the experiment. And this is the following idea. So let us assume, of course, we're going to idealize, so to make the math very simple. Let us assume we have two plates, and these are infinite plates, and they have their surface is A. That's the size of each one of them. This A goes to infinity because I don't want to calculate really complicated things. And here I have a charge density. This is not the sigma of the J equals sigma E. This is the charge per unit area. Charge per unit area. So this is going to be a high school lesson. This is minus sigma. So these are negatively charged. This is like a very simple problem. And we are going to allow, but what we are going to do is we are going to allow this guy to move. But let us allow it to move, but very, very slowly. There's no magnetic fields in here. Because the currents go to zero practically. And what will happen to this? So this guy is fixed. It cannot move. How do you do that? I bring some hammer and some nails and I stick them on the wall. It cannot move. Or there is something a frictionless thing that can move it in this direction. So what will happen? This guy is positively charged. I keep all along. I keep this charges the same, and this guy is negatively charged. So what will happen to this second wall, the left wall? It will be attracted to this one, and there will be at the beginning we put it at velocity 0. At the end, it will have some velocity. Why? Because there is some force acting on this thing. It's high school, right? You can imagine what is this force. Now, we will soon calculate it. I'll do it soon. So this is the start, and then after some time, I'll stop the experiment when they collide. Some T max. Okay, now I want you, and we can calculate how long it takes, all these things. Everyone in high school can calculate these things. But now let us think about this from the point of view of the energy. So what is the energy here? You have energy here. This is zero energy, kinetic energy. At the end, there is some final kinetic energy that we can calculate. Okay, is this clear? But now let us think about the electromagnetic fields in this problem. So at the beginning, what is happening here? This is at the beginning. There is some E inside here, which is easy to calculate. Here, what is E? 0. And here is E is equal to 0. This is also something you learned in high school. Because one of them is positively charged, the other one is negatively charged. Outside, inside they are creating the same electric field in the same direction. That's why it's pulled in this direction, right? And so this is the starting point. And what will happen at the end?
They will collide and then there will be no field.
So the field in this process went away compared to the beginning and compared to the end. Now, what is the claim before I do this exercise? Inside here, there is a field. If there is a field, electric field, which is constant, because we want to think as simple as possible, if there is an electric field, there is electric field density. I can integrate here and find out what is this electric energy. And what is the prediction of all this theory?
That the work done on the left plot will be the energy density over
Right,
the
so the kinetic energy at the end of this plate should be the same as this. So this is a way to understand how you transform energy, which is electromagnetic energy, to simple kinetic energy. Okay, that's the idea. Now let us do this. It's not difficult because this is there is only a small minor point to think about, but we can do this and we can check this. This is what I want to do now, and it works. Believe me that it does. And this is a kind of proof that indeed the field itself, this E at the beginning here inside, contains something which I can call energy density. I can move it into kinetic energy in this case. You can say that in this problem I don't need the concept of energy to calculate things. I can do it with forces, which is absolutely true, but it's also true for many other problems. So also when you drop a ball to earth, you can say, okay, the force is mg, or you can say I'm transforming energy of the given by the height to kinetic energy. It's the same thing, of course. So this is what we are doing here. So in this case, it's not really useful to get anything new information, but it is useful to understand this concept. So the idea is, okay, so let us just do it kind of hopefully quickly. Minus sigma. So what is the field here? If you calculate it, it's sigma over epsilon 0. In this direction, this is E. Now there is one plate. One plate, you have this 2 epsilon 0. So this epsilon 0 here is the sum of the two things, and here it's divided by 2, and this 2 is actually important. You saw already 1 over 2 in the equations, but without this. And why is this important? Because this, if this is the, let's say this is the minus 1 and this is pulling the plus 1, the plus is feeling not its own force, right? It's not pulling itself in the air. It's feeling the force created by the other one, by the other plate, which is created by this electric field. So this is 1. So, okay, let us do it the usual way, the high school way. This is, okay, you first say what is F. I think the direction is very clear. It is sigma times A. This is the total charge, because the force is the total charge multiplied by the electric field. The electric field that the left plate field is this with this 2 sigma over 2 epsilon 0. It's in the z direction. That's the z direction, and this is equal sigma squared A 2 epsilon 0 z. What is V? What is this V? That's the V of the plate. It's simply A, it's in the z direction, times T. This is the kinematics, and this is equal to F over M times T. That's Newton in the z direction. The reason, what I used here is the V0 is equal 0, so you start from rest. Because we don't want to calculate the difference in the kinetic energy, we just start at 0 and then what is this? When do they hit? Or let's call this. So okay, I want T max. T max is at the end of the process. I don't have to do that, but again, T max is when you close just before the collision, if you want. And this you know, this is D, is A T max squared. This is also kinematics. You know, V0T plus a usual thing. And D is the initial distance that we had here. So I can find, because I know A, how do I know A? A is F over M, and F is, this is F. I know A, I know everything here in short. And then if I calculate this, I'm not going to do this, the kinetic energy, which is M, you need to add the mass of the thing. If you want to think about it, the mass goes to infinity and A goes to infinity together, and they cancel to something finite. So this is V final squared over 2. F is for final. And this is simply given after simple work, MAD. And this is obvious, because this is like the kinetic energy. What is this like? You have MGH. So you start MGH and you go down. Instead of G, you have A. What is A is related to the electric field. So all this equation is, it's not mad. It's not that I'm mad, but it's mass times A times D, like MGH. Simple change of kinetic energy, and this thing like in a gravitational field, a simple gravitational field. So if you want to be explicit, if you plug in the A, it's M the thing is that this M will cancel this M. That is important. And this AK I can show easily sigma squared A 2 epsilon 0 times D. Yeah. Now we can calculate also what is the loss of electromagnetic energy, and it has to be the same. So it's very simple. E electromagnetic is the following. Now we need to use not sigma over epsilon, like here, 1, we need to use this one. So it's sigma over epsilon 0 squared multiplied by d tau epsilon 0 divided by half. The half comes from the half that we had before. And then all this is a constant, and this guy is equal to sigma squared. What is d tau? It's just this volume. It's A times D. So it's sigma squared divided by epsilon over 2 A times D. And then I'm very happy because they are the same. See, these two guys are the same. So it works. At least it works in this sanity check. Yes?
Aren't we supposed to have linearity in D, in the electric field, as the
D? Well, D, this D?
D as in the distance between the plates, because the plates get closer and closer, and the electric field is supposed to grow.
No, because they are infinite plates. They are infinite plates.
Ah, okay.
If they are infinite plates, the field inside is a constant.
Yeah, okay. Regardless of the spaces between the plates.
This is my assumption. They are infinite plates, and then what happens is minus sigma plus sigma. The physical picture is this guy goes on top of this guy. Of course, in reality, there's a small layer in between, but then these two charges are canceling each other in some sense, and then there's no electric field.
Yeah, no, I just, if they're infinite.
Yeah, no, they are infinite. This is idealized. They're totally idealized.
Yeah, okay.
Now, let us. Okay, so. So now we had. Okay, so one more example, which hopefully will be interesting. So now we wanted to understand these energies in a problem that, okay, this problem you know more or less, you can solve it from high school, but now I want to show you that what you study in high school, maybe also in university, is actually very partial. So now let's do the simplest thing we can imagine, and that is we have a pipe and we have some J, constant J, and we have, because we have some current here, right? We have some heat created. So you'll touch it and it will be very warm or not. And this heat has to be related to the energy influx, this balance that we had before, fields created. Now, first question. First of all, there is inside this wire, which is interesting and where a lot of physics is going on. Sometimes we cannot measure inside, and that's a different story. And there's the outside, where we can measure. So we want to connect these two worlds. So the dissipation is happening here. And then the question is, where is the energy flying into the system? Where does it come from? So, and secondly, what are the fields here? So what are the fields here? If you have a constant current in a wire, infinite wire, what are the fields?
We have inside.
No, outside. Let's start from outside. Inside is also trivial, and let's assume that it is a linear system. So J is proportional to A, and we are given J. J is fixed.
We have mu 0 I over 2 pi r.
Here, there is magnetic field outside here.
Mm-hmm.
Anything else?
Electric.
Lambda divided by 2 pi.
There's no lambda. There's no charge on this thing.
No charge. Okay.
So this is the problem that you learned many times. You have an infinite wire. You are using the right hand. You get a magnetic field. It decays like 1 over r, exactly as you said. But then what? That's the end of the story. But actually, that's not true. I mean, this law is correct, but there is also an electric field outside here. Even though that there's no free charge, there's nothing. And these electric fields, so out here there is both electric field and magnetic field. We'll soon explain this. And this is super important. If there is electric and magnetic field up here, then there is energy density up here, right? This is what we studied. And then there can be some flow of energy into the system. We have to think, how does it flow? How does the energy come into this system? How do I know it coming in? Because it's heating. So if there is dissipation, if something is going away, something has to compensate it. So how do you think the energy is going to come into this system? In which directions? So the way most people think about this simple problem is, okay, we have here some battery, right? There's a battery here and it's attached, and then you are pushing electrons in this direction like a pipe. So the energy is like flowing like this. It's not what happens at all. It's totally wrong, and actually the main statement here, if you want a kind of statements, current in wire is not like current of a fluid, which is not charged, I mean, in a pipe. So in a pipe, let's say you have a pipe. You want to transport some water from there to there. You have a gradient of pressure, right? And then the water goes, and then the water molecules have kinetic energy, and you push them, and then they go, you open your faucet, and then you get water, right? With electromagnetic fields, it's totally not the case. What will happen, I'm going to show this, where does this energy come from? It comes from the energy, electromagnetic energy up here and down here, and it goes into the system like this. So outside of this wire, you create electromagnetic fields, and these pump in energy into the system. This is what Maxwell tells us. It's not that I have, let's say, an electrode and it's like a pressure gradient and it goes like that. Even though this analogy that I just said is totally wrong, it's very useful to calculate things, some things, like I and things like that. It's good to think about it. This is what they tell you in high school, but it's totally wrong. Now, the energy is coming in from here, as I will show. So what is happening here? We have a very complicated process for physicists, not for chemists. For chemists, this is very easy. What are the energies, the types of energies that we have here? We have the heat, I mentioned. We have the electromagnetic energy, and then we have this, what? The
velocity of the charges.
The velocity of the charges will go into the heat, which are colliding, so there's a constant heat.
The potential.
We have the battery, of course, that is driving all of this, and this, let's call it chemical potential. It can be from many sources, but let's call it chemical potential. So what is happening here? The chemical potential is creating magnetic fields here, and these are transferring it inside to this. This energy is dissipated because the batteries are not interacting here. There are no batteries inside, they are far away. So the batteries are here, they're creating electromagnetic fields here, and then the energy is transferred inside. It is dissipated by collision, and these three sources of energy are changing all the time. So it's not kinetic energy and height energy, it's three energies altogether in a concert. So I'm not saying it's trivial, but when you think about it, eventually it is very beautiful, because why does the energy come in here? So another thing is, we want to calculate this dissipation here. So you can do it, you know, we did it already. No, with Ohm's law, we did it. We did it in high school. And now I'm going to do it in a really crazy but beautiful way. I'm going to do, instead of calculation inside, I'm going to want to calculate outside. And this I can do because the integrals over the electric fields are outside. I can do it outside, extending these integrals that I had before. So I'm going to do that and get information from the electric fields and magnetic fields up here on the dissipation inside, because these are the transfers of energies, electromagnetic to heat, and electromagnetic comes again from the battery, but the battery is not directly related to the heat. It's this cycle. So if you think you don't need to think about it, you're wrong. You need to think about it with your friends, with your, I don't know, your girlfriend, your boyfriend, whatever. With ChatGPT, it's not trivial. Now, why is this so important? Because if you are able to transfer energy from up here into the system, then of course this is related to technology. This is kind of obvious, I think, but this is at least how people started it. So let us do this rather simple exercise and show what is going on here. So what I want to do here is as I mentioned already, J dot E, this integral over these things, that's this dW dt, the heat, the power, is equal to this integral that I can do outside, because J is outside here is 0. I can do this integrate over the fields, essentially over S. Why over S? Because the fields themselves are not changing in time here. The current is constant, so here I have this E squared over 2, but now the time derivative is equal 0, because E and B are constants, because this is a steady state. So the only term now we need to consider is this flux of energy. So what is this flux of energy? Okay, so first of all, what is S pointing? I'll write it just, this is going to be outside the wire. So it is E cross H. But outside the wire, H is which is just B over U0. There's no material outside. So, and what is H? H, this is, you know, up to this 2 pi A. This is A, this is this radius. This is the famous equation that was discussed before. There's no mu 0 because I'm talking here about H. So this ace, okay, so first of all, inside there is an electric field in this direction, same direction as the J. How do I know that? That is the Ohm's law. J equals sigma, not the sigma here, E. So to get a J, you need an E. You are inside here. Why do I know that there is an electric field outside? I know it for two reasons. If there will be no electric field outside, what will be the S? 0. There will be no supply of energy, which would be terribly bad. So there must be E, but this is not a proof, of course. How do we know that there is an E outside? So the same E, if this is an infinite wire idealized, is also up here. Why is this happening? Div E is equal 0. There's no free charge in this problem. What is rotor A?
It's B.
Minus the B dt, but what is B? What is this? This is equal 0 because the current is constant, there's no time here. It's a steady state current. So you see that rotor E is equal 0. What does these two equations mean? It means that you have here a Laplace description of E, like in statics, but it's not exactly statics. You still have a J. And in particular, the usual thing, if I go along the pipe, I have here E parallel, which is the E in this direction. Let's call this material 1, and outside is 2. This is E2 up. And the line integral, as usual, has to be 0, because of rotor E is equal 0, which means E1 here and E2 here are the same. So what you studied even with me, I cheated a bit when I said in magnetostatics, you have a field outside, yes, but you also have an electric field. For example, what is the consequence? Let's say I put here a charged test particle with velocity equals 0. You think that there's only magnetic field, nothing will happen. But what will happen in practice, you have also an E, it will accelerate, and then the magnetic field will act and it will move. So this is a very different description when you translate both of them. Now, did I cheat before? No, but there is something subtle in the teaching. When we teach electrostatics, we say there's no J. Then we teach magnetostatics, we say there is a J. But then we need to go back and correct the E. It's not statics, and this is what I'm doing here. So there is a constant field, and this is the same as E. There's no jump. So what is the picture? The picture is we have some E. And do we know this E? Yes, because we know the J. If we know the sigma of the material, we know this E. And we have a magnetic field. So how is the magnetic field? H or B are the same because we are outside. How is the magnetic field operating? This is the right-hand side. The right-hand rule is going like that, right? So the J, the B is like this. This is the direction of B. You see, this point is an arrow hitting you. That is the direction of B. This is what you know in high school. The addition is this E. Important thing is B is perpendicular to E, which is not new because we already showed in a different scenario, but B is perpendicular to E also here, maybe not so surprising. But more important, now I can calculate the vector potential. If I have E dot B, where is S?
S is pointing up.
Like that. E dot B,
Yeah.
E dot B, S.
We are calculating it just on the boundary, or is it decaying over the distance of the wire?
I'm doing everything.
Everything?
If I want. Of course, B will change with distance, but this direction B and this direction E E is a constant because there is it's a constant for all space. Yes, so this is amazing, but because the wire is infinity, that's not trivial, but it's true. For an infinite wire, for finite wire, it will be only close to the wire. So how do I know this? I know this because of Laplace, because if E is a constant and then it solves Laplace because of this rotor E is equal to 0, then this is the solution and that's it. Okay, that's the uniqueness of the solution of the Laplace equation. I'm using here things that we learned at the beginning of the semester. But the point is that S is like this. It goes down, so just to draw it again, but only the S goes like this. But no, but you had a very good point. Here I plot the S, if you want to think about it, because I use the B outside on the surface. But it doesn't matter, because the direction of S will be the same. The value of S will change because this H or this B is decaying with distance, but it will be the same. Okay? The direction will be the same. And actually, when you will calculate the total flux, it will not matter where you do it. Because this decays like 1 over r, but when you talk about the total energy, you will need, instead of, let's say, this A here, you'll need a ring, which will be depending on your distance, and this will cancel out. So it doesn't matter. So this is what I say I'm doing ever. So I do it close to the surface, but I can do it up here. I can do it anywhere. And it will give you the same result. It will give you the heat inside inside the material. So this is the direction of S. So what is a wire? What is a wire with current? When you think about it deeply, okay, on one hand it's carrying current in this direction, but what is a wire in this point of view? Can you summarize it in a sentence? It's an object that directs energy into electromagnetic energy into it. It's guiding the energy to come inside. But that is what the wire is doing, guiding electromagnetic energy into the material. Again, everything that you studied previously is all totally correct, but now we have this kind of new picture. It's not a practical picture because we don't have new predictions, but if something is going inside this energy, then we can get excited, as I mentioned already many times, because the next step is to make this practical. Then you need engineers, not physicists. Physicists just think and do nothing. Engineers do real things, right? But once you understand this, you can start thinking about applications where you move energy. And then you can be rich, not like physicists that are always poor. Because you don't go to the work festival. You remain poor like Einstein. Right? Well, unless you get some prize or something. No. The life of physicists is not so bad. So let us calculate this S. Just what is it? It is I over 2 pi. I do it on the surface. This is the H, which is equal to the B. Again, it's a bit outside. Then I need to calculate the E. I now write it like in high school, voltage drop over L. This is E. And we know the direction. I described the direction already. Now, we have this. This is the energy per unit time, per unit volume. Now we need to multiply it by the volume. What is the volume? To get the total energy. It's 2 pi A. It's exactly the same here. This is the answer to you. So if I would make the surface 2 pi r outside, this would be r, and then I'd have to calculate the total energy on that bigger surface. It will just cancel out. 2 pi a multiplied by L. This is when I have, because what is the 2 pi a? So because the magnetic field is going like this, what am I calculating at the surface is like that, right? This is the wire and this is this outer surface, not this one and this one. The outer surface that is going here, this is the surface that I'm talking about, which is 2 pi a multiplied by L. L is this distance, principal going to infinity. This is the surface area. And this gives you the total area. So S, if you want dA, integration is equal to I times V, which is what you know in high school. Because 2 pi a L goes away. And this is the usual power, the change of energy that is dissipated into the heat. So we calculated everything outside. We got a trivial result in the sense that this is known in high school, but we totally changed the picture of the physics of what is going on. And because we didn't change yet any prediction in some sense, so you can think, I know everything. That will be absolutely totally wrong. So please read chapter 7 and 8, and we will have more examples a little bit in the next lesson. We'll see how Einstein took this and started creating relativity a little bit, and then move on to other things. Okay, so thank you very much.
שמעתי על כל מיני תוכניות של סינים, על פאנלים סולאריים בחלל שמשדרים אנרגיה לכדור הארץ. ואם אנחנו כבר דיברנו פה על אנרגיה של גל אלקטרומגנטי, ניסיתי להבין בגלי מיקרו וזה, אני פשוט רוצה להבין איך בכלל זה אפשרי לקחת פאנל ולהצליח לשדר אותו כמות אנרגיה שיכולה באמת להפעיל משהו.
אם אתה שואל האם באופן פרקטי או באופן עקרוני? באופן עקרוני זה אפשרי, האם באופן פרקטי אני לא יודע.
באופן עקרוני, אבל איך עושים את זה?
באופן עקרוני, לדוגמה, יש לך שמש, ויש לך לדוגמה בעיה ידועה, מפרש.
מה, אתה לא מעדיף לזה?
אז אתה אומר, יש שם רק קרינה אלקטרומגנטית בגלל האור שנפלט מהשמש. המפרש הזה, אתה מתחיל אותו במנוחה, אתה יכול לחשב, תשאל את ChatGPT.
בעיות של פיזיקה מודרנית,
זה לא מודרני, זה אלקטרומגנטי.
לא, שחישבנו כאילו במבוא המודרנית, שפוטונים פוגעים במפרש ודוחפים אותו, זאת הכוונה.
כן, אבל אתה עושה את זה עם מקסוול, לא עם פוטונים, לא עם H בר אומגה. אתה יכול לעשות את זה עם מקסוול, ואז יש לך שטף E קרוס B, יש לך S, ואז הוא נושא גם תנה, לא דיברנו על זה היום, אבל הוא נושא גם תנה, הוא מתנגש נקרא לזה במראה המושלמת. אם אתה יכול ליצור מראה מושלמת זה שאלה אחרת, ואז המפרש הזה או המראה הזאת יתחיל לנוע במהירות מסוימת. זה אנרגיה קינטית.
אנרגיה קינטית שקיבלנו מהגל אלקטרומגנטי.
כן, מהקרינה של השמש.